Good afternoon, everyone. My name is Claire Ajiman. I am one of the two co-directors of the Institute for Molecular Science and Engineering. Nick Harrison, the other co-director, is sitting just here. And it's my great pleasure to welcome you to this event tonight, the launch of our latest briefing paper on the development of antimicrobial surfaces. We have the pleasure of having a few of the authors of the paper here in the audience, and you'll hear from some of them today. But also there'll be a chance to talk to the others over drinks later on today. So the Institute for Molecular Science and Engineering was established a few years ago to really try and build on rapid advances in the understanding of molecular interactions, our ability to characterize and model what they are, and to try and bring that understanding to bear on societal problems. So we're an institute that focuses on grand challenge-led research, and we bring together teams of people that are multidisciplinary teams and try to motivate them to work on these grand challenges and to bring together their knowledge to address them. And so we do this in a number of ways. Of course, we put together research proposals, we run research projects, but we also do other things to try and catalyze this research and our understanding of what is needed. One of the things we do is we run a master's program where we bring together engineers and scientists to try and develop a multilingual approach to developing solutions, so to bring their different perspectives together. And another thing we do is these briefing papers, the one that you have in front of you today. And we're very proud of these papers. They help us to define a problem, but also to think about really how we can have a true societal impact, how our research can reach into policy and into technological solutions to those problems. And so tonight we're going to hear from two of the authors about the development and the findings of the paper. And then this will be followed by a panel discussion with participants from a range of backgrounds, okay, so that we can get these different perspectives. So our first talk today will be by Dr. Gerald Larry Momus. Gerald, please, if you join us. Before I hand over to Gerald, I just want to highlight our hashtag for tonight, which is Imperial Smart Surfaces. So please feel free to tweet as Gerald tells us about the findings of the paper. Gerald, thank you very much.
Good afternoon, everybody. It is my great pleasure to welcome you, and on behalf of the co-authors, to thank you also for coming, because it has been quite a long process, to be honest, this briefing paper, and a great adventure, which I'm very happy and delighted to present this afternoon. So my role, I'm a microbiologist and biochemist working at the CMBI, which is Center of Molecular Bacteriology and Infection, so basically microbiology. And my role of this afternoon is to tell you a bit what are the main take-home message from this briefing paper. Then it will be followed by John Otter, who will discuss a bit more about the applicability of those what we call smart surfaces in clinical settings. And of course, there is no doubt you're all aware about the threat of antimicrobial resistance. Along with climate change, global warming, antibiotic resistance is one of the bigger threats humans will face this century. And therefore, we have to act here, we have to act now, because if we do nothing by 2050, just to give you some figures, nowadays, it's sad to say, around 700,000 people die yearly from antibiotic-resistant bacteria. If we do nothing, by 2050, 10 million deaths will be attributed to antibiotic resistance. And we know from the news, the headlines every morning, that infectious disease not only impact on health, but also on the economy. We see with the coronavirus. And of course, we have to think about this in the future, looking at antibiotic resistance. By 2050, if we do nothing, it will cost a loss of more than $100 trillion. So looking at not only we have to work on having better health, but also to support the economy. And of course, this is good to say we have to play the economy, and that's to be from government, because these are the ones who have power to change things. Of course, we remember what I presented the slide earlier, the report from the British economist Jean O'Neill was back in 2014 already. And just last year, the government has launched a new 5-year program for UK, including with those are the three main objectives. The first one is to reduce the need for an unintentional exposure to antimicrobials. The second is optimizing the use of antimicrobial. This we can think about better diagnostic, for example. And the third one, and this is the most important one, is to continue to invest in innovation. And that's why in innovation, Imperial College is the best place to tackle this threat of antibiotic resistance. Under the banner of Antimicrobial Research Collaborative, which was launched a few years ago, it includes researchers from different disciplines, such as medicine, including engineers for Faculty of Engineering, and life scientists, such as microbiologists, belonging to different centers, such as Imperial BRC, Biomedical Research Center, National Heart and Lung Institute, NIHR for National Institute for Health Science, and for example also the CMBI, which I discussed with you briefly, the role of CMBI, fundamental microbiology covering microbiome, immunology, basic bacterial physiology, and of course antibiotic resistance, meaning that we know tackling antibiotic resistance has to be a collaborative effort, cross-discipline, ranging from medicine, microbiologists, and engineering. And that's why with IMSI, back in time, a few years ago, with this in thought, we say, right, we know there is a great initiative happening within the college. We know that IMSI is best placed to have this cross-discipline approach. What can be the strategy to merge this discipline? And we have identified smart surfaces. And we organized back in time a workshop where around 40 attendees were at this workshop, and the morning, for example, was about a talk from a world-leading expert, and the afternoon was about brainstorming. Brainstorming about, right, you know, we are engineers, we know we are Faculty of Medicine, so we know that we are microbiologists. How we can brainstorm and get something together, putting this briefing paper. This was the seeding adventure of this briefing paper you have in front of you this afternoon. And this was co-organized by Professor Omar Matar, which is a chemical engineer, and myself. So you see cross-discipline. And of course, sponsors were back in time EPSRC, so Research Council, because again, it's good to have ideas, but it's good also to have a support from Research Council, support from industry to have a real impact to tackle antibiotic resistance. And now I want to present you the main discoveries, or not discoveries, the main take-home message for antibiotic surfaces. Of course, we have to know that bacteria are living organisms. Bacteria, they like to form biofilm. Biofilm is what is representative here, this picture. Bacteria are what we call, in first phase, planktonic, and then they go to form biofilm. Even antibiotics can work very efficiently when bacteria are in planktonic form. Then you can see on this picture, bacteria, when they're in biofilm, can be protected from antibiotic. Why? Because they are able to produce extracellular matrix, precluding the antibiotic to reach the bacteria which are just at the surface of the, for example, a hospital bed or a water pipe. And this makes the antibiotic efficacy decreasing drastically. And again, in those biological or extracellular matrix, which is composed of extracellular DNA, polysaccharides, it makes things worse. And when we think about smart surfaces, we think about the first step, which is adhesion of the bacteria. It's like the bacteria, you have to think that it's like a table tennis ball bouncing around, and at some point we'll have adhesion attachment. What we want is to preclude that. And what is described in the briefing paper is the three main strategies, which I will present you a few examples. The first one is inspired by Mother Nature. It's about what we call nano spikes or nano needles. For example, this is what is found in the cicada wing, on the surface of cicada wing, which is an insect. And if we zoom those wings, it's a small dots, which are around 1 micrometer. And if we zoom a bit more, we can see those called of nano spikes. If the bacteria is on a smooth surface, it's very happy. She likes smooth. But if the bacteria is having some like a rough surface, nanospikes or nanopillar we call, then the bacteria will feel quite uncomfortable, and those nanospikes or nanoneedle will puncture the bacteria and therefore will lead to the lysis of the bacteria. As you can see here, the bacteria saying, ouch, I don't like, this will cause cell death. And in fact, we have to think, right, this is very elegant because nature or biomimetics are very good, but the downside is how to manufacture this in a large case, how to manufacture some in a surface which is affordable. Some solution exists, such as silicone-based polymers, for example, but we have to think we need to have scalable. Again, the main advantage, we have to think also the positive side. The advantage is that this is non-specific, meaning that bacteria which are susceptible to antibiotic and the ones which are multi-drug resistant will also be affected by those nanospikes. And this is what we call contact killing mechanism. The second surfaces is very common, is using metallic ions such as copper. And we all maybe have seen those kind of vessels. And I remember back in my childhood, my grandmother making a plum jam in those components. And it's not random. Why? Because copper is a self-sanitizing material. And because of that, people were using heavily copper back in time. Copper has been used for millennia by mankind. The first traces of the use of copper was from Egyptians' time, then the Greek. And it's quite interesting because if you look at the word copper, in Greek it's called Kypros, and Kypros means is where it comes from the Cyprus island, because back in time it was where this island was rich in copper. And therefore then people were using this a lot and then went a bit down, and just back in the 19th, 20th century people reusing again copper, because we have to think that bacteria cannot develop resistance to copper because it's intrinsically linked to the mechanism of action of copper, as you can see on the slide. In A, if you have bacteria lying on a copper surface, copper will be solubilized, will enter the bacteria cell. The second, in panel B, what will happen is membrane rupture, meaning that all the components of the cytosol, such as ribosomes, will be leaked, meaning that the bacteria is lysed, then you have production of radical oxygen species in C, and in D will cause DNA damage. And when we think of DNA damage, meaning that there is no transmission from a parental bacteria to a daughter bacteria. There is also damage on plasmids, so no transfer of plasmids, such as plasmid resistance. So we think that copper is a great tool, but when we see copper is a limited resources, and because it's limited, then the price increase, and we have to think developing a smart surfaces about middle and low-income countries. So that's the reason why we need to develop material which have the same properties as copper, but has to be affordable and as well as widespread and easy to manufacture. And the last one is the self-cleaning and self-polishing surfaces. This is very interesting because what I described before is more flat surfaces. The other one can be thinking about water pipes. We know that in hospital, the main source of contamination is water, and notably bacteria such as Legionella or Xenomonas. And what we would like to develop, what is the idea, is to have a surface which is repelling the bacteria, precluding the bacteria to attach. And this could be, like as I said, bacteria are bouncing on surfaces. And so what we want is the bacteria still to bounce and get out of the water pipe, for example. And this surface can be composed of material which contain a biocide for the bacteria that are still able to attach and self-cleaning. So that are the three main take-home message for this briefing paper. Overall, we have to think that you could have seen that there is no magic or no universal smart surfaces yet, because, of course, we need to have much more research to that area, and we have to think also into a translational aspect to be affordable for not only countries like the UK, but also middle and low-income countries. And again, I will never insist enough about investing in innovation and, of course, cross-disciplinary, such as what we are doing here at Imperial. So now this is the end of my talk, and I will hand over to John Otter, who will be talking more about the applicability of smart surfaces in healthcare systems.
Thank you, Gerald. Well, good afternoon, everybody. Thank you for coming. I know everybody's crazy busy, but hopefully we'll get some value and some interest out of this event and the time we have this afternoon. So as Gerald has said, I'm going to take those ideas and those concepts of how we could make a surface antimicrobial somehow and see where they could be applied in a clinical environment to reduce healthcare-associated infection and antimicrobial resistance. But I'm going to start with a cauliflower. And I'm going to tell you about one of the most remarkable studies I've ever read. It was published in 2000, and it was a very simple idea to try and illustrate the challenges of the inanimate environment in healthcare and show how important it is in the transmission of bacteria and other microbes. So they did a very simple thing. They took some cauliflower DNA that they knew the sequence of and knew wouldn't be common in a healthcare environment. They inoculated a single telephone receiver in the pod, a single pod of a neonatal unit, and then they sampled the environment over the next 72 hours to see what happened to this tracer. And what they found was, I'm clicking the wrong way, that's what, I'm clicking there and the computer's there. What they found was, over the course of the study, this marker went everywhere. Most of the surfaces in the pod that was inoculated, but even where it wasn't inoculated, over this relatively short period of time, there was a huge level of contamination. And here you can see how quickly it happened within 4 hours. This little marker was everywhere across the unit. Now, okay, it's a DNA marker. It's not a microbe, but it's not too far removed from a very simple virus in terms of its structure. Now, I actually rang up this research team that was in America, and I said, why didn't you do any more? Because it was just this one study published in 2000 and then nothing else. And they said the ethics committee said they couldn't do any more because they were worried this cauliflower marker might recombine somehow with the human genome. Cauliflower DNA, often found in cauliflower. Anyway, more recently, some other researchers in America have taken up this idea and done some really elegant, beautiful work tracking the transmission routes, including the healthcare environment. And you can see clearly, if you had some kind of antimicrobial surface on that telephone receiver, if that was made of copper, this wouldn't have happened. There's a little known fact amongst even expert colleagues that work in hospitals, and that is that if you're admitted to a room where the previous occupant of that same room had certain types of microorganism, so for example, MRSA, C. difficile, Acinetobacter, then the risk of acquisition for patients admitted into that same room is doubled or more. Isn't that amazing? And slightly terrifying. Should we be asking, well, hang on, who was in the room before me? And how is it disinfected? And these are the sorts of questions that we need to ask that may be coming. But again, it illustrates that if we can improve the ability to remove contamination, particularly at the time of patient discharge, we'll mitigate that increased risk and improve outcomes. So this is what we're looking at trying to do. We're trying to take the touch surfaces within a clinical environment and make them antimicrobial somehow. Now, this has been done to a fairly large degree. So you see the similarity. This was a study performed in the US quite a few years ago now, and they changed 6 touch points in the room, one of which was the bed rails, from plastic or whatever they were made of to copper. And then they did a randomized trial to see whether that intervention resulted in reduced healthcare-associated infection and reduced acquisition of key marker bacteria. And this is what they found, that there was around about a 50% reduction in both healthcare-associated infection and the acquisition of antibiotic-resistant bacteria, just by changing this relatively small number of touch surfaces in the room. And the major academic criticism of this study, and there has been, as you would expect, major academic criticism, was that that scale of reduction is too big to be biologically plausible, which is quite circular, isn't it, as a kind of criticism. There were some methodological challenges. The study isn't perfect. But as a proof of concept, it's pretty powerful. Now, if we go into a hospital room in this country, in the hospital where this was done, or anywhere in the world, we're unlikely to find it copperized. And that's because if you take your boiler out and all the pipework at home, you'll make some significant money from the pipework. Copper is an expensive commodity. So I think if this approach is going to be implemented in this way on a mass scale in the clinical environment, we need to have a much more cost-effective process. And who wants to sit on a copper toilet seat? So there's some patient acceptability issues that we need to think through as well. So that's one of the 4 application areas that I'm going to mention briefly. The idea of touch surfaces in the healthcare environment. We've also got the idea of medical devices, sort of related to that, indwelling prosthetic devices and the hospital water and plumbing systems, all of which I think are ripe for this concept of making surfaces antimicrobial. So let's look at medical devices. This area is a little further developed than the idea of antimicrobial touch surfaces. There's some really quite impressive work on silver-coated urinary catheters and their impact on reducing catheter-associated UTI. This was a study, again, published many, many years ago now. 2000, when's that? Is that really 20 years ago? So it's quite a long time ago, and yet, again, this hasn't been implemented in the mainstream, I think, for issues mainly of cost and economics. So you can see here the silver-coated catheters, the UTI rate was just over 2, the uncoated catheters just over 3, and a significant reduction in their primary outcome of this randomized trial. They also did some interesting economic modeling where they said, yeah, okay, these catheters are more expensive, but because of this scale of reduction and the cost of dealing with catheter-associated UTI, we think on balance this will have a net benefit to the healthcare system, and yet still not implemented, at least not widely. So smart indwelling prostheses, I would say this is the most developed of the 4 areas we're going to talk about today. There's been lots and lots of candidate technologies that are either on the market, in preclinical or in clinical trial, related to this concept of a device that goes into the body that didn't start life in the body, somehow making that surface less able to support microbial contamination and therefore reduce the risk of subsequent infection. And you could look at all of those and put those into the 3 buckets that Gerald told us about in terms of the way that they approach trying to make a surface antimicrobial. So this is one study of many where they showed that in this randomized trial of a hydrogel coating on prosthetic hips and knees, they found a really quite dramatic reduction in SSIs subsequently. Although the numbers in the study were fairly small, it's quite a convincing outcome. Smart plumbing. Where could we apply these systems in the hospital water management system? One area, well, I couldn't find much information about antimicrobial surfaces applied in this way, which suggests to me this is an opportunity because it is a problem in healthcare settings. What I did find was some experimental evidence that contamination with things like Pseudomonas and Legionella in this environment are challenging and difficult to manage. This study shows simply that Pseudomonas grow much more effectively and survive much better on plastic flexi hoses than they do on copper piping. And of course, there's a big commercial driver not to put copper piping in because it's so much more expensive than plastic. And yet, there's some government guidance actually saying, please don't put in these flexible hoses that support Pseudomonas biofilm so well. Look at copper piping, ideally, and if you must, straight plastic piping. And I think there's certainly potential for improving the surfaces of the internal surfaces of the pipework so that we reduce the risk of things like Pseudomonas and Legionella in healthcare settings. This is what we're trying to do. We're trying to maximize patient safety. We have some evidence already that by somehow making a surface antimicrobial, we can reduce contamination in a number of different areas in terms of touch surfaces, in terms of the medical devices, in terms of prostheses, and in terms of the hospital plumbing systems. And in doing so, there's evidence that we will improve patient outcomes. We have a unique collaboration and an opportunity here to create the kind of multidisciplinary environment that this problem requires, because it's not just microbiology, it's not just engineering, it's not just chemical, it's everything together. What I'd love to see is the emergence of some kind of platform technology. That's what we're shooting for, that will cover all of the application areas and will merge a couple of those different modes of action. So, for example, a surface that doesn't support microbial contamination as well as others due to its physical structure, but also exerts some kind of antimicrobial activity. Those are the kind of questions we need to come up with. And the white paper here, in the modern world, you don't often get to lay your hands on something that's been done, so it's quite nice to see it printed, so thank you for that. It largely describes some of the things that we've talked about, but it presents the problem, it doesn't present the solution. So that's what we're here for, is to talk about how we can get to some solutions to these challenges in the healthcare setting. Thank you.
To John and Gerald for an enlightening overview of this briefing paper. Thank you. So now we'll move to the panel discussion, and there'll be a chance to ask John and Gerald and others some questions. So if you could please, if the panel members could please join me at their seats. Thank you. So we're very fortunate to be joined by people from academia, but also bringing an industry perspective, a personal perspective, and a government and funder perspective. So I will first ask our panel members to please introduce themselves. So Phil, if perhaps we can start with you.
So I'm Phil Packer, I'm from Innovate UK, and I'm the innovation lead for AMR and vaccines. Essentially, Innovate is trying to develop innovative ideas to increase the UK economy. So essentially, we're funding mainly business to try and develop new, exciting science, which will help the UK, both in its practical utility and in financially in the future as well.
Thank you. Tracy.
And I'm Tracy Parker, and I'm Head of Policy at the Department of Health and Social Care for AMR, Healthcare-Associated Infections and Sepsis. So it's my team that coordinated the 20-year vision and 5-year national action plan that the government published about a year ago. And right now we're moved into implementation mode. So we work across government and its agencies to implement all the commitments in that plan. And we have something like 8 separate delivery programs across the 4 countries, because it's a UK program, and we're starting to get on with implementation and achieving the ambitions that we set out.
Thank you.
Hi, my name is Chiara. I'm just literally finishing up my PhD in the Department of Chemical Engineering, and I founded a company called BrightCure. Maybe you've heard of it. We are trying to develop a novel approach to prevent and treat urinary tract infections, especially recurrent infections that a lot of women are suffering from. And I had huge issues with this, and this was the motivation to start BrightCure.
Thank you, Alison.
Hello, I'm Alison Holmes. Gosh, this feels like on University Challenge or something. And I'm reading. I'm a professor of infectious diseases within Imperial College. I've benefited enormously from funding from the NIHR, the EPSRC, and the ESRC. I'm a director of a health protection research unit. And really enjoy this kind of cross-faculty, multidisciplinary working. Within the NHS, I'm a infectious diseases consultant, and I'm a director of infection prevention and control.
Hello, I'm John Otter. I have a role in the NHS where I manage the infection control team in one of the London hospital groups. I also have an academic role at the college looking at healthcare-associated infection and antimicrobial resistance.
Hello, I'm Gérald Laruy-Mormus. I am a senior lecturer in Department of Life Sciences, and as you have seen during my talk, we work at the CMBI, Center of Molecular Bacteriology and Infection, and what our laboratory is interested in to understand, first of all, why bacteria become resistant, so very fundamental aspect, and the second part of the lab is to develop new diagnostic solution using one of the workhorse found in clinical lab, which is mass spectrometry.
So, well, thank you very much all for joining us tonight. So I'll start by asking perhaps a few questions to follow up on the talk and see the perspective from all panel members. So you've, of course, talked about surfaces and possibly multifunction for surfaces. What are your reflections in terms of the role of surfaces together with other approaches to AMR? What is the specific role of surfaces there, and how can they work in tandem with other strategies?
So if I can start. Surfaces are a very small part of the practice in a healthcare setting of reducing the risk of infection. If we absolutely nail surfaces and do nothing else, it's futile. So it needs to be seen as a package of measures to prevent transmission. But on the other hand, I would say that the role of surface contamination in transmission is almost impossible to disentangle completely from the other possible transmission routes. So if you have patient A to patient B, it's almost impossible to know how the bug got between the two patients. And it's likely to involve transient contamination of surfaces and hands and equipment all in together. So in one sense, although we make a distinction between hand contamination and surface contamination, hands are really another mobile surface in a healthcare setting that isn't disinfected as often as it should be.
Yeah, and if I can add, smart surfaces is one part of the puzzle within what we should do, like diagnostic, better use of antibiotics, and that, and we should not think at only one part on its own, but as a multidisciplinary again and complementary approaches.
So we're focusing in acute healthcare because that's certainly our backgrounds, and I think later on, of course, the conversation can talk about the community and other surfaces and livestock and food production, and I think we need to consider that in the environment. But just sticking with acute healthcare, which is where our major focus is, I think we also need to think about how we look after people. I mean, we're bringing in the most vulnerable people. We're putting them all in close contact. We're exposing them to the biggest amount of antibiotics, either to them or to the person next to them. They're the most vulnerable. We're giving them the highest risk of developing antimicrobial resistance, surrounding them with opportunities to get to acquire or transmit antimicrobial resistant organisms. And we have to take care of the surfaces that are directly around them or that we put into them. That must be part of how we minimize risk. We also need to take care of our staff that work in these environments and think about their health and safety as well. But the other opportunity I don't think we've touched upon enough is the really powerful combination of the engineering, but also of the engineering in terms of the design and thinking about human behavior and our opportunities, not just in terms of the nature of the surface, but how we could maybe design out surfaces, minimize touch points, be smart about that as well.
Tracy, I wonder if you have any comments in terms of the role that surfaces play in your strategy.
Oh, well, absolutely. I mean, our strategy actually covers 15 different areas, including food and water and sanitation and animal health, antimicrobial use. But fundamentally, in our country, our resistant infections continue to go up. We had 60,000 in 2018. That's a 9% increase in the year before. And really, really interestingly, Lord O'Neill published his report in 2016, and the government set an ambition then to halve our healthcare-associated gram-negative bloodstream infections, our most worrying kind. So though we've had national programmes and a national focus since 2016, they continue to increase. So I think the challenge is not small, and I think when there's lots of discussion amongst the experts and policy people and those trying to implement, and very often the problem is, well, they're all coming from the community, but actually we haven't reduced them in hospitals either. So, this kind of thing, and exactly what Alison said, is precisely, what we need, and the strategy just does set that out. It does talk about, we need to look at how we use the built environment to prevent infections.
Okay. And so, as we've heard, surfaces, you have some hopeful solutions, let's say, to the problem, but there's no magic bullet, right? Gerald, you highlighted some challenges with each approach. Do you have any thoughts on what priorities we might take moving forward? Should we just explore all areas, or are there any specific areas that you think should receive more attention?
Priority should be based on what the feedback from what people like John are getting and where is the most appropriate, and not only it's about the challenges in manufacturing those surfaces, because you have a great publication that stay in academia, but the transfer to scalable is way more challenging. That's the reason, and I see personally where will be the challenge going from the bench to the bedside. For example, that would be one of the major challenge to transfer. Again, we want developing a smart surfaces or antimicrobial surfaces that is affordable and not restricted to hospitals or clinics which can afford it. And on the opposite is to have more spreading these technologies, and notably for middle and low-income countries. So that will be then the major challenge. And after, as you mentioned again, the challenge of having a smart surface which is applicable to a large panel, not only restricted to a particular disease, for example, a particular intensive care unit.
Yeah, I'd reinforce that. I'd go back to this idea of the platform technology. The first question should be, could this approach be one that could be widely applicable in a range of different areas? If not, do we need to go back to the drawing board now and look for that kind of thing first?
Mm-hmm. Okay. And so
I was going to say, do you think that we've actually properly tested any of those potential ideas? The reason I'm asking that is because, so I'm lucky enough to deliver some work for Tracy, and we had a call out on AMR, and we did actually put infection prevention and control in that call, because we thought it was an area that we hadn't really addressed properly. And I have to say, we didn't really get many applications in that area at all. And I do think that we need to actually now try and actually test something rather than do research, try and get something out. And, well, you'd have to do research, but to take it a little bit further, do get it into industry and try it out, because I know it's not very sexy, and that sounds awful, as well as a topic. People much prefer to spend money on antimicrobials than they would on a new surface. Yeah. But I do think it'd be useful now to let's try and test something. Let's actually try and push something. And I think we might have to do some more health economics, which you mentioned earlier, just to demonstrate what this could actually achieve if it was working. Sorry, what's it in there?
No, that's great. That's great. And Chiara, did you have any thoughts on this? Because you are trying to bring this to practice.
Yeah, I mean, mine is a bit different, because I'm trying more to develop a therapy that actually patients would take. And I think one big factor here is also in terms of my whole experience with this, because I suffered from 9 infections per year. Right. I was resistant against some antibiotics, and I think one issue is for sure in terms of urinary tract infections, the whole diagnosis also around it, and the whole education. I think education is a big factor, and I think also lots of people, they're not really aware actually how dangerous this problem is. I think they always think, oh, there are some antibiotics, and I just go to the doctor and I get a prescription, but actually it's not like this, and it will not continue to be like this in the future. I think there's not this pressing need yet in a way that people realize that we actually need to work on this. I think when it comes to the surfaces, in terms of like the whole patient pathway, that I always need to think about, especially also when I talk to investors and say, okay, how applicable is this actually to real life situations? Where are patients going if they suffer? What is the first point where they go to? Do they go to the pharmacy? Do they do online prescriptions? Do they, I don't know, somehow. So I think when it comes to smart surfaces, it's really nice in a way that you can probably more easier implement it than trying to develop more like a drug or a therapeutic for it, because you can just test it. In terms of the surfaces, I now not directly in touch with it, but where I specifically actually looked at it was at the beginning, before I pivoted a bit. The idea was when I was looking into far UV light, far UVC light, and the use of far UVC light, and also when it came to the catheters that we also talked about, because this is obviously catheter-associated UTIs are a huge issue, and literally every patient who has a catheter, indwelling catheter, gets a UTI. And so there are different solutions, bladder flushing solutions, that we also look into for adding this as an additive. But one idea was also the light and how you can design the catheter in a way that you could reduce these infections.
So I would say we've had lots of applications for UTI, for treating UTI, but nothing on the catheter side at all, as far as I have seen. Okay. So I just think we're just not seeing the applications. There possibly is a technology there, but we haven't actually seen it coming through beyond research into sort of early stage into business.
So that's a great call to arms for
us
all.
Well, yes, yeah.
I wonder if there are questions from the audience for our panel. So we've got some roving mics.
Yeah, sure.
Let's see which one gets there first.
Thank you very much.
Go ahead.
I'm just really curious, where does data fit into all of this?
Data.
You mean about smart surfaces, how it could affect? So just...
No, I mean, like, for example, are you collecting any data and analyzing any data, with regards to bacteria, that kind of thing?
So in terms of data, I think data management and enhancing the latest tools could definitely give us the edge. So there was a study published last week, you may have seen in the media, using machine learning to screen a huge number of candidates to develop antimicrobials on a drug discovery path. We could take that learning and perhaps apply that, tweak that process to identify possible candidate antimicrobial surfaces. So I think there's options for doing that kind of thing. There's also the idea of mathematical modelling to try and understand transmission routes and pathways and how effective antimicrobial surfaces might be, and extending that to add economic components to begin economic modelling before we've even developed proper implementable surfaces.
And within healthcare, to use data, to use as much data as possible from patient pathways, geospatial mapping in terms of persistent and recurrent infections in certain hotspots when you can't identify, is it a person, is it a reservoir from a patient, a member of staff, or is it something to do with the environment? So there's many ways that that data from healthcare can be tapped into. It won't ever give an accurate solution, but we could be using that much more effectively as well. And certainly it could be integrated into research programs where we're wanting to test particularly different bits of intervention related to the surface, but also to the design of the environment.
Thank you for a talk on something which relates to today's very problem of coronavirus. But I was fascinated to see that copper has these antimicrobial properties, but of course if you use it in a prosthesis such as a knee joint or hip joint, it has no wear properties at all. And one wonders how that's going to be compatible to a properly engineered prosthesis. But also, you haven't really defined what kind of bacteria we're talking about. Is it both anaerobic as well as aerobic? Because anaerobic, as you know, is regarded as the most toxic and resistant of all antibiotics. And antibiotics themselves seem to be very dominated by introduction of chemicals. And I put this to Sally Davis a couple of years ago, that we need to look back to organic origins. And she did agree, we look at penicillin, that's lasted a very long time. We need something like that, where the body doesn't reject new elements into the properties of modern antibiotics.
I totally agree with you, and of course, with the amount of time we have this afternoon, we could not go bacteria by bacteria, but basically, what we have presented, and notably, for example, the nanoneedles or nanospikes or copper, in fact, it's just about the duration of killing, basically. We can think about the gram-negative bacteria, like Pseudomonas, or gram-positive, like Staph aureus, or even the worst-case scenario about tuberculosis. And basically, what we want is having surfaces which works not only on one bacterial based on the gram, so gram-positive one, but cross bacteria. And again, it will depend on, first of all, the question we're asking. If we're in a care unit, in intensive care unit or hospital, okay, we know that we want this population of patients is more prominent for Legionella or Pseudomonas. So maybe we should have a design of surfaces that take into consideration this aspect. After, of course, what we want is something universal, and that's why not only having bacteria which are susceptible to antibiotics, but the ones which are already drug resistant, because that's the one we should pay attention. It's not the one susceptible, we know how to treat. It's the one which are already resistant and that spread. And that's the one, especially when we think about polymyxin resistance recently rising drastically, carbapenem resistance, we think about multi-drug resistant TB, and it's also particular bacteria we should focus. And of course, when we think about trace elements, again, you have variabilities. When we think about having antibiotic like penicillin, and of course, we need to go back to basic microbiology and look at which in fact, because now humans have used a lot of pesticides and fungicides, and it will be going more complicated to find those natural products. And of course, the challenge in antibiotic research is to find new class of antibiotics and maybe go back to these natural products. Nevertheless, as John mentioned, the paper in Cell published last week, which used artificial intelligence to generate new chemical compounds that are able to treat not only gram-positive, not only gram-negative, but also mycobacteria, for example. That is a type of approach to take. But this, again, was a very important paper for the field, but we have to think about the development of such technology and such chemicals, for example. So again, is to have a combination of multidisciplinary research, and we should, as maybe you mentioned, never forget the basis. And maybe John or Alison can complement.
Yeah, I was just thinking about the particular challenge in healthcare setting, which is bacterial endospores, so Clostridioides, now so-called difficile, or C. diff, which causes a nasty antibiotic-associated diarrhea. And part of the problem and why it spreads so effectively in healthcare settings is because it spreads in the spore form, which are notoriously difficult to inactivate through disinfection. So trying to find an antimicrobial surface with sporicidal activity, that will be a challenge. We may need to do some tweaks of the surface somehow to do that. You mentioned durability and the kind of surface finish of copper in certain applications, and I agree that's a challenge, certainly. And that's where we need our material scientists and chemists to use the latest tools to give us the engineered surface finish that we need.
Thank you. There's another question here.
Well done on your briefing paper and presentations today. This might be a question for Tracy, Alison, or Phil. I want to explore how much enthusiasm you think there might be in clinical practice for reusable surfaces. Hands, for example, are an example, as you've given, of a reusable surface. But so many things we dispose and then incinerate. So, yeah, it's around reusable surfaces. Do you think there would be any enthusiasm for a smart reusable surface, tubing, etc.?
The answer for me is if there's evidence that it doesn't contaminate and is safe, then I'm sure there will be. Simple as that, I think.
Yeah, I think so. And interesting, that same question sort of indirectly was asked at a meeting I went to a while ago. Everything is disposable these days, and we're creating another problem by having everything disposable. So it might be the right time to start looking at reusable things. I think it's something we should be thinking about. Yeah.
But I think there would be enthusiasm, but I want to go back right at you and talk about that the design is absolutely critical, because what you want to make sure about is that in that reusability, you're not creating more touch points or more opportunities for self-contamination. So, the whole issue about like masks in the news, but actually how dangerous they are if you contaminate yourself, and how the issue about taking on and off personal protective equipment, the risk of that if you don't do it properly because you contaminate yourself. So, I mean, that's an extreme example, but I just want to kind of point out that great reusability, but however, absolutely has to be risk-free in terms of the patient, but also in terms of the healthcare worker. But we are sticking with acute healthcare a lot, and I wonder also if there's an opportunity to talk more about the environment or livestock in areas that are beyond our expertise, but opportunities there. But I do think it's important when we're talking about, somebody asked about priorities. So there's something which is about the kind of here and now, and the kind of emergent, the issue about looking at your level 3 care, your neonatal intensive care units, your adult intensive care units, where people are their most vulnerable, where you're shoving the most surfaces and foreign bodies into them, and you're also exposing them to the most antibiotic resistance. So that's a kind of really urgent, emergent, really, really needed. It's an immediate priority. However, there are issues which are kind of more medium to long-term priorities, which is about how we can reduce continued transmission in the community, in livestock, and in food production as well. So I think we need to look more broadly than the immediate, although the immediate is something, of course, of great interest to us at the moment.
And so to what extent do you think the basic concepts that you've presented in terms of surfaces are applicable to different settings, like the food industry, for example, where biofilms are a significant cost as well as a health issue?
So I think in food production, absolutely critical, and major opportunities, and not with great expense, but so in food production, but also in how we manage livestock, we need to think about surfaces a lot more. And I think there's many opportunities there. I'm not sure in terms of grant applications and proposals, but I think ways of avoiding antibiotics. I mean, if we're talking about, vaccinating fish and salmon so that we don't use antibiotics, I mean, there can be other ways of looking at how we can prevent biofilms, etc., in the environment and in food production.
There's actually one interesting example, because we're looking at a predator bacterium, so it's actually completely microbial approach in a way, because it's a predator bacterium that preys on gram-negative bacteria, and they literally eats them and kills them. So the idea is to kind of overcome the recurrent use of antibiotics, and basically also breaking out of this vicious cycle of infection, antibiotic resistant, another infection, and so on and so forth. And when it comes now to the food, because we just touched that, is that in China they actually use this predator bacterium in shrimp farms to avoid in aquaculture the use of antibiotics, which is very interesting.
Yes, Tracy.
If I can chip in on the livestock point, I think that is absolutely crucial. And in this country, we've reduced our use of antibiotics in livestock by 53% in 5 years. That's an incredible amount. What we don't have is data on the impact on infections. So we do need to work on our biosecurity in farms, and we need to do those things alongside. But absolutely, there's a huge need for that, and to maintain that low use, it's critical.
So what's been used to counter that reduction in antibiotic use, or was it just excess use, or have there been some new techniques that have been used to
Well, it's the responsible use of medicine is just set standards for good practice of use of antimicrobials in farming, and all the sectors have risen to the challenge voluntarily to deliver that. But we are at that point where the reductions are plateauing, and we do need to do that kind of research to see, has that had an impact on animal health or productivity and profitability, and we need to do much more focusing on now the biosecurity element, because any further reductions would be through preventing the infections.
Some more questions over there?
Hi, thank you so much for this report. I was wondering if you can shed some light on the progress that has been made on, for example, surfaces like copper. In terms of chemistry-wise, have they seen a huge development, or have you seen like a very tapered approach where they have reached to copper and that's mostly it, kind of thing? And the second question I had was following up on the comment that Alison just made on chronic kind of infections where people are forced with like stents and catheters and so on. Do you think that these surfaces would stand the long-term test of how they interact with the human body as well?
So I can answer the first part of that around the development of copper surfaces. Most studies are using copper as copper in a fairly simple, unengineered way. So I think there is potential progress in looking at developing the idea and taking the best bits of copper and turning it into something that's cheaper, perhaps more durable and perhaps more acceptable to patients. Some groups have gone some way down this road, but I think there's further to go. In terms of the durability of a antimicrobial surface with a medical device, I think is largely untested at the moment. Alison, do you?
No. I think though that there's a really interesting question that you're posing, which is about the duration that we're, the duration of these embedded devices. So, a while back, we would be thinking that hips and knees would be maybe 20, 30 years. I mean, so now the kind of what we're expecting and what we're demanding of prosthetic material is really quite extraordinary. But I also want to go back to what we said about it's not just the surface, it's about reducing it. So anything that we can do to kind of reduce the surface of a foreign body in a person is absolutely critical. And also, not just things that we're, not just in terms of surfaces of implantable devices, but also when we think about how we minimize surfaces by keyhole surgery and minimize things by using robotic surgery, laparoscopic surgery, all of these things that reduce surfaces in terms of wounds, in terms of contact with other surfaces is all really important. So the design and the minimizing of the size as well as the engineering of the surface itself all need to be brought together.
Okay, thank you very much. We're running out of time, so I just wonder whether you have any parting thoughts as members of the panel, thinking about us as an audience, as researchers or as members of the general public, any take-home messages for us, one thing we should do to perhaps stop or reduce microbial infection. Tracy?
I did want to just say something at the end, not quite answering your statement there, but I just wanted to go back to something that Cara said, and I think she's absolutely right about messaging. And while we've had, this is something we do need to get right at the national level, we've had our singing, dancing, antibiotic campaign, which Public Health England will say it met its objectives, but no one knows what antimicrobial resistance is still. It doesn't really mean anything to anyone. But I think stories about people with infections that actually blight their lives and going into hospitals and coming out with infections. And what fascinates me, if you look at the graphs of where we are with E. coli, Klebsiella, Pseudomonas, compared to MRSA, which everybody knew about for a while and was very careful about cleanliness and being cautious in hospital, the E. coli numbers are way, way above where MRSA ever was. But that isn't on people's radar at all. So I think there's a lot more we could do to raise awareness so people start demanding surfaces, different ways of doing things in hospital and elsewhere. And that'd be my parting shot.
Thank you. Anything else?
I just wonder about, we've focused a lot, so in terms of human healthcare, in the acute environment. So I think we need to recognize that we need to think about the community and also in our long-term healthcare facilities, and we need to be a little bit more joined up when we look at risk and where the potential of addressing AMR through surfaces could actually lie. So I think looking at the whole healthcare economy, from our community care, long-term care facilities to acute care, tertiary care, we need to look at it all, as well as the One Health approach that we mentioned earlier.
And of course, we mentioned healthcare, but we have to think about the day-to-day and the routine life, which is a transport, like handrail and all that aspect to take to consideration, because it's not only reducing resistance in the healthcare system, but also outside the healthcare system and bringing not out for in and in out. Okay, so that will be the major issue, and also having a surfaces that can be implemented not only in hospitals but outside the hospitals. That will be the ideal case scenario, which in fact can reduce considerably the spread of resistant organisms.
So I would say that we are here having this conversation because nobody's really cracked this as a problem. So we need to get our heads together, pool some brain cells and come up with some new ideas and some novel ways of thinking, pulling in the unique expertise we have to take this forward.
So that's something that Innovate UK are meant to help with. So perhaps I can talk to you about that, because what we have done in other areas, we hold workshops and try and bring people together to try and create things. So that might be something I can have a think about.
Yeah.
So I think it's clear our panel members have found the conversation stimulating. I certainly have, and I hope you have found it inspirational as well. I'd like you to join me in thanking all of our panel members for their conversation tonight and their insights. Not over. We will have drinks outside, an opportunity to discuss some more, as well as some posters if you want to find out more details about the research that's going on in this space. But before we go out to the drinks and posters, I'd like to say a few more thank yous. So in particular, I'd like to thank the authors of the briefing paper. So we have a few here today. Perhaps if you could stand up so that people can find you downstairs as well. Yes, and Jason and Nick as well. So thank you very much. The reviewers of the papers, so Alison, you were one of the reviewers, Jimmy Moore and Alain Filou as well. Thank you very much for contributing to the paper. And then I'd like to thank Leah Adamson for her work on organizing this event. I think she's probably out already making sure everything is set up downstairs. And also Kieran Brophy, who led the development of this paper and made it happen. Thank you, Kieran. And finally, thank you all for coming tonight, and I look forward to talking with you downstairs.